Let's take a look at a couple of examples involving translation and rotation. In this example, we have a cylinder, radius 0.1 meters, and a mass of 25 kilograms. And there's a string wrapped around this cylinder, and so the string will pull the cylinder to the right. The string then goes over a massless, frictionless pulley. That's located here, so we're not going to have to worry about the rotational energy of that. And actually the problem doesn't even state that it's massless, but since it's frictionless, the movement of the string is not going to be able to rotate that pulley. Also, the tension in the string will be the same on the left and the right hand side. And then I have a 12 kilogram mass here, which is hanging 1 meter above the floor. So I want to start this problem out by writing out the energy equations with an energy bar graph. And since I'm going to have an energy bar graph, let's set the datum for this problem right here at the floor. And so when I do that, I'm going to have an initial kinetic energy for the cylinder, and we'll have translational kinetic energy for the cylinder, and rotational kinetic energy for the cylinder. We're only going to have translational kinetic energy for the hanging mass, and then we'll have gravitational potential energy for the hanging mass. Now, since the system starts from rest, only the gravitational potential energy has any value here. And then once the object has fallen and reached the floor, I'm still going to have translational kinetic energy for the cylinder, rotational kinetic energy for the cylinder, translational kinetic energy for the hanging mass, and gravitational potential energy. Now that will be 0 at this point in time. So you'll notice I have 5 blocks on the left, so I'm going to need 5 blocks on the right, and I'll distribute it that way. I don't really know if that's the way it is ratio-wise, it doesn't matter. So the equations that go along with this, I'm going to have 0 plus 0 plus 0 plus the hanging mass times g, and we're going to say that it starts at distance y equal 1 meter above the floor, so I'm just going to call that y. And then once it reaches the floor, there's going to be the kinetic energy of the cylinder, so 1/2 the mass of the cylinder times the velocity of the cylinder squared, plus 1/2 the rotational inertia of the cylinder times the rotational velocity of the cylinder squared, plus 1/2 the mass of the hanging mass times the velocity of the hanging mass squared, and then 0. There's no longer gravitational potential energy. Now we're given that the hanging mass is 12 kilograms. We're given the mass of the cylinder is 25 kilograms, and we know the moment of inertia of the cylinder is 1/2 m r squared, so that's 1/2 25 kilograms times 0.1 meters squared. We know the cylinder is rolling without slipping, and so there's an instantaneous center right here. The cylinder is moving with the velocity v at the center of mass, and so the velocity of the cylinder equals the radius of the cylinder times omega of the cylinder. So I can find omega of the cylinder, which is this term here, in terms of the velocity of the cylinder. Now the velocity of the string, notice that the string is a distance of 2r, so the velocity of the string is equal to 2r times omega of the cylinder. It's a distance 2r from the instantaneous center. And so the velocity of the string is twice the velocity of the cylinder. And the velocity of the string is the same as the velocity of the hanging mass. So now I have the velocity of the hanging mass in terms of the velocity of the cylinder. So everything in this right-hand side can be written in terms of the velocity of the cylinder. So there's only going to be one unknown when I do that substitution. And so I can use that in order to solve this equation then for the velocity of the cylinder. And so I might rewrite the equation as 12 kilograms times 9.80 meters per second squared times 1 meter. So that's going to equal 1/2 the mass of the cylinder, which is 25 kilograms, times the velocity of the cylinder squared, plus 1/2 25 kilograms times 0.1 meters squared. There's the moment of inertia of the cylinder. And then omega is the velocity of the cylinder over 0.1 meters. I square that. Plus 1/2 12 kilograms times twice the velocity of the cylinder. And I square all of that. So if I calculate this out, the velocity of the cylinder turns out to be 1.66 meters per second, which means that the velocity of the hanging mass is twice that, 3.32 meters per second, and omega of the cylinder is equal to the velocity of the cylinder over 1/10 of a meter, so 16.6 meters per second. So energy conservation using rotation and translational kinetic energy, and then also gravitational potential energy is what we use to solve this problem. I can rerun the same problem using forces. So I've got gravitational force here, mg, normal force, frictional force, tension, and over here I've got gravitational force, tension. This is going to be accelerating to the right, mass times the acceleration of the cylinder, and there's also going to be an I omega in the clockwise direction. This one's going to be accelerating down, hanging mass times the acceleration of the hanging mass. And I'm just going to go ahead and right away state the acceleration of the hanging mass based on the string arrangement again is twice the acceleration of the cylinder, so 2a sub c. We use a standard xy coordinate system, and if I write out the sum of the forces in the x direction, I'm going to get T minus F equals MAC over here. Sum of the forces in the y direction, I get Fn minus mg equals 0. So the normal force is simply equal to gravity. And if I do the sum of the moments about the center of gravity, I'm going to get Tr minus Fr equals minus I alpha. Minus because I alpha is in the clockwise direction. So I need to change this. This is I alpha, not I omega. Now if I look over here at what's unknown, I find I don't know the tension or the frictional force or the acceleration of the cylinder. I don't know the normal force, although that's just mg, so let's go ahead and count that as known. And I don't know alpha. But since it's rolling without slipping, I do know that A is equal to R alpha, and that would be the acceleration of the cylinder. Now I can't say that the frictional force is equal to mu times the normal force, because it's not an equality, it's an inequality. And so it could be anything less than mu(s) times the normal force. Although I could check to make sure that it's not greater than mu(s) times the normal force to make sure it's rolling without slipping. But I don't know mu(s), so we'll just assume that it's rolling without slipping and that F is less than mu(s) times the normal force. Now over here in the y direction then, I have T minus the hanging mass times G. Same T, so I have not added another unknown here. And that's equal to minus the hanging mass times 2 times the acceleration of the cylinder. So I haven't added another unknown. So I have 1, 2, 3, 4 equations in 4 unknowns. And so I can write T minus F minus 25 kilograms times the acceleration of the cylinder equals 0. I can write 0.1 meters times T minus 0.1 meters times F plus I. But I here is 0.125 kilogram meters squared. So plus 0.125 alpha equals 0. A minus 0.1 alpha equals 0. That's A equals R alpha here. And finally, T plus 24A, that's from here, 12 kilograms times 2, equals 117.6 newtons. So I need a change here. That's minus T. If I solve this system out, I get the acceleration is equal to 2.751 meters per second squared. Then V squared equals 0 squared because it started from rest, plus 2 times 2.751 meters per second squared. That's 0.5 meters. If I solve that out, I get V is equal to 1.66 meters per second. And you'll notice that's exactly the same as what I got here. And so whether I use energy techniques or kinematics, I still get the same answers. And that's a nice check. Okay, so let's take a look at this problem. I'm going to address this problem using conservation of energy or the work and energy principle. I'm actually going to use conservation of energy, but notice that there's energy dissipated by friction. So on the left-hand side of my energy bar graphs, there's going to be work done by friction, and that's what I'm interested in. What is that energy dissipated, or the work done by friction? Now you'll notice in its current position it's rising because I have a counterclockwise angular velocity of 4 radians per second. And we're interested in what's going on when it's in its vertical position. But notice the vertical position here is 12 radians per second for an omega. Now that means that it can't be this position here, because as it rises in this direction it's going to slow down. So it must have gone all the way around to where it's hanging down into that position. And that's going to be important. So let's take a look at the energy in this situation. I'm going to have a translational kinetic energy for gear B. I'm going to have a rotational kinetic energy for gear B. I'm going to just look at the energy of AB as it rotates about point A. So I'll use the parallel axis theorem to find that moment of inertia. But that means I just have a rotational kinetic energy for AB. Now both AB and B will have gravitational potential energy. There's no springs in here, so I've covered all of my bases that way. But there is going to be work due to friction. Call that U sub F. So there's translational kinetic energy in all of these cases. I'm going to set my datum right here at 0, so there's no gravitational potential energy currently. And then work is going to be done by friction. Alright, so I've got 5 bars of energy on the left. And then over here later on, when it's in the vertical position, I still need to have 5 bars, but there's not going to be any work done by friction. That's already been accounted for. So I have the translational kinetic energy and the rotational kinetic energy of B, the rotational kinetic energy of AB. And then VG of AB and VG of B, those are both downs, and so I'm going to need to still have 5 bars. Notice I've got 4 bars down, so I need 9 bars up. So I'll put it something like that. Alright, now I need to put equations with this. So if I look at AB, of course its center is right here, and that's fixed. And then gear B has an instantaneous center here. Because the ring gear here on the outside is not moving, that point on gear B must be motionless, at least at this instant in time, so that's the instantaneous center. So what that means then is that the velocity of B, which is in this direction, the velocity of B is equal to the radius of B times omega of B. But the velocity of B is equal to the length of AB times omega AB. And I can get then information about these relationships from here. And what I want, I'm going to put everything in terms of omega of AB. So the velocity of B is equal to L times omega AB, but that's also R omega AB, R omega B. And so I can say then that omega B equals the length of AB over the radius of the gear B times omega AB. And then there's going to be translational kinetic energy for gear B, but I've got that right here. So the velocity of B is just going to be the length of AB times omega of AB. So in the beginning, the translational kinetic energy of B is 1/2 the mass of B, which is 6 pounds over 32.2 feet per second squared, times the velocity of B, but the velocity of B is R, which is 2 inches. So 2 inches is 1/6 of a foot times omega B. And I'm going to square that. So there's the translational kinetic energy of B, and the rotational kinetic energy of B, plus 1/2. It's a 6-pound gear, so 6 pounds over 32.2 feet per second squared. Radius of gyration is 1.2 inches, so that's 1/10 of a foot squared. So there's the moment of inertia times omega of B, but omega of B is the length of AB over the radius of B, so that's 4.8 over 2, so we're going to call that 2.4 omega AB. I need to square that. So there's the rotational kinetic energy of gear B. Then the rotational kinetic energy of AB is 1/2, 1/3, the mass, 3 pounds over 32.2 feet per second squared. And then the length is 4.8 inches, so 4.8 over 12. That converts it to feet, and we'll square that, times omega AB squared. And keep in mind, I know all of the omega ABs here are 4 radians per second, plus the work done by friction, which will be negative. And all of that's going to equal the final kinetic energy, which is these same 3 terms. So it's this term, and this term all over again. Only now I replace omega AB, which was 4 radians per second on the left-hand side of the equation, with 12 radians per second on the right-hand side of the equation. So everything is numbers. I'm going to substitute all those in. The only thing I don't know numerically is the work due to friction. Solve that out.